Now, in this problem, it's a little bit complicated because we have a source that's emitting a sound. It's bouncing off of a moving block and coming back towards the original emitter, which is also a detector. So it's kind of seeing how the sound transforms in frequency as it bounces off of a moving block. If whenever you get a reflection problem for a Doppler effect, you're going to essentially have to use the Doppler effect twice. The first one is when the sound gets emitted from the emitter and hits a block where the block is thus the observer. The block is going to see a change in the frequency of the sound, but then it's going to reflect the sound and then become the emitter. So the block will first observe the sound and then re-emit. So that's what a reflection is where you observe it and re-emit. You're going to re-emit the sound back towards the detector. And that's the two parts. The first part, the block is the observer, but the second part, the block is the emitter back to the final detector. So we use the Doppler effect twice. F1 in this case is going to be the frequency that the block hears before reflecting. F naught is going to be the original frequency of the sound. And then F2 is going to be the frequency that the emitter detects once it bounces off the block. So we're going to essentially see that the block takes that frequency, re-emits it, and that re-emitted frequency is now the source frequency. And that's why I'm putting it as F1 down here, where this is the place of the source frequency when something emits to an observer. That being the case, because the block acts as a different agent in both these equations, these variables that say observer, source, are going to mean different things based on which equation we're using. So the first thing I want to do is write down the equation and use something that's more friendly towards our particular problem so that we can actually do this more efficiently. Second thing I want to talk about is that the top variable, or sorry, the top operator is for situations where the observer and the source are moving toward each other. So if you look back in the notes, you'll see that the equation calls for using the top operator where things come toward each other. F1 is equal to F naught times the speed of sound V, top operator is a plus, and we're going to use the V observer. In the first situation, the observer is the block, so I'm going to just call it V block. Divided by V minus, because that's minus is the top operator here, V source, which happens to be, I'll just call it source. Second equation, now the block is the emitter because it's reflecting sound back towards this now detector. You're going to reflect the new frequency that the block heard back towards the detector, that's F1. You're going to multiply it by the speed of sound V plus. Now, the observer is in this case the source again, which then acts as the detector. V minus, and now source is the block. So now we have this, and now we have it in terms of descriptive subscripts that relate to our particular situation. So we don't have to worry about these equations anymore. Now we could put these two together without worrying about the differing variables based on the situation. Now what we can do is we can simplify a little bit before combining. The source never moves. So for both cases, I'm going to make the source 0. Now let's go ahead and combine the equation by putting this into that. F2, which is the final frequency heard by the detector, is going to equal to F naught V plus V block divided by V. Okay, and this is F1 right here. And then after F1, you have this bit right here, and this is going to be V divided by V minus V of the block. And there you go. That's the final equation that you need for this particular situation. So now you only need the velocity of the block coming towards the source detector, the speed of sound and air, and the original frequency. The original frequency is 5,000 hertz. The velocity of the object is 3.5 meters per second. And the speed of sound in air, we're going to go ahead and say is 343 meters per second. Now, if you plug all this in, you get the final frequency as 5,103 hertz. If you want to do a logic test, it should be more because the sound is being Doppler shifted blue and is coming back as a Doppler shifted blue. So it's going to be blue shifted both ways. And that means it's going to have a higher frequency times two, I guess. Okay. So to speak. So 5,000 is the original frequency, came back as 5,103 hertz. That makes sense because the block's coming towards it. So it's pushing the waves together to create a higher frequency.